Last time, we pretty much finished everything that you need for the lab this week. There is one point I want to make, and this is with total internal reflection. If you have like a material like water and air, if the light is, say, exactly perpendicular to the surface, the light will just simply pass through from one to another. If you travel at an angle, what you begin to notice, if you're going from water to air, that the angle of incidence and the angle of refraction differ. And for this particular case, you've got to use Snell's law. N1 sine theta 1 equals N2 sine theta 2. And this deals with refraction. And we covered the ideas of the principle of least time, principle of least action, the saving of the puppies. And really what's happening is that to get from that point to that point, it's not a straight line, it's got a bow a little bit because it travels more slowly in water than it does in air. So if the theta of incidence is less than the critical angle, you get this. If the angle of incidence is equal to the critical angle, what happens is the light doesn't necessarily refract or reflect. What happens is that the light, that as it hits the surface, travels parallel with the surface. So if that is the angle of incidence, then the angle of refraction is equal to 90 degrees. So what ends up happening is you've got N1 sine theta 1 equals N2 sine theta 2. Theta 2 is equal to 90 degrees. Sine theta 2 is equal to 1. So what ends up happening is that the equation N1 sine theta c is equal to N2. So sine theta c is equal to N2 divided by N1. So theta critical is N2 divided by N1. And in this particular case, water is my N1 material, air is my N2 material. Oh, sure. Oh, that's a great question because I haven't finished it yet. Inverse sine right in there. So let me write it more professionally. So it's like that. So at the critical angle, the light that is refracted is at 90 degrees. It's running parallel to the surface. At yeah, equal. Say that again. Glad you asked. for angles of incidence greater than the critical angle, what happens is you get reflection. And with reflection, you get the angle of incidence is equal to the angle of reflection. So that answers the question. So angles less than the critical angle, you get refraction. Angles that equal the critical angle, you get that line. Angles greater than the critical angle, you get the total internal reflection. And so those are the three situations. Now notice for critical angles to exist, one must travel from a medium of a higher n to a medium with a lower n. And you all know how much I don't like writing words, that is. So if I actually wrote it out, then this must be kind of important. In order for this total internal reflection to occur, you're traveling from a medium of higher to lower, such as, and the critical angle equation is this, or you could say that the critical angle is the inverse sine of n2 divided by n1. If n2 is less than n1, then n2 over n1 must be less than 1. So let's think about, in all your days of dealing with the sine function, if you take the sine of anything, what's the largest number that you'll ever get? 1. If you've been dealing with sine for a very long time, what's the smallest number or the lowest number that you'll ever get? -1. So it's always between those two values. It will never exceed a magnitude greater than 1. So if n2 was greater than n1, n2 divided by n1 is greater than 1, and theta c, which is the inverse sine of a number greater than 1, is impossible. It goes crazy. So it is physically impossible for light to internally reflect off of going from air to water. The light will pass in. And one of the things that, when you look at this in terms of observation let's just look at that green line, which is really an important part. If you have water, and let's say we're hunting the fish of fury, and that is the actual position of the fish of fury, and your eyes are looking down at that fish, what really happens is the light that you see from the fish is the light that's refracted through the water. So in order for you to see that fish, if you see that fish, the true location of the fish is a little bit lower than where you're looking. So if you were spearfishing, the image of the fish is green as far as you're concerned. So what you do is you aim a little bit lower. And so what's really interesting is that the indigenous people, the people who spearfish on a regular basis, just inherently know to aim below the image of the fish. If you actually have, like, say you have a broom, or if you're cleaning the pool and you take the anything with the pole on it, you put the pole in the water, what happens? The pole moves. Not moves in the sense of moving around, but it bends. It ends up in a weird location. It doesn't look straight. Another thing that happened was, I live in University Trails, and one of the interesting things about the pool is it's got Ole Miss in tile at the bottom of the pool. And I could see it from my windows. And then, in an effort to clean the pool, they drained the pool. And I'm out on the porch looking at the empty pool, and suddenly I realized that I could not see the Ole Miss writing. And what happened in that situation is that if you could think of this as the edge of the pool, Ole Miss is written down there, it bends and makes a steeper angle so that I could see it. I was actually looking around the edge of the pool so that I could see the bottom of the pool. With the water not there, there was no refraction, and so the image of the pool, the light from the image of the pool goes straight, and it's blocked by the edge of the pool. So refraction does have real world examples. So the biggest thing so far that I've talked about today, spearfishing, why you can't have total internal reflection from one medium to another if the medium you travel into is a higher index of refraction. All right, now, in today's lecture, what we're really here to do is talk about mirrors and lenses. And with the first thing we're going to do is we're going to talk about mirrors. Mirrors reflect, obviously. If you had, this is one of the questions I think they ask still in the lab. If you have a mirror and you have, here's your little stick figure. What is the smallest mirror possible where you could actually see your entire body? Yes, in the back.
Half your height.
Thank you. Why? Let's talk about why. Did they talk about this in lab? Huh? The ray diagram? All right, well then I'll just do it in 10 seconds. Thank you for the spoiler. So there's a virtual image over here. The light that he sees is like this, so that you could erase that bottom part of the mirror and then you could still see yourself. So this part of the mirror is unnecessary, all of these parts. Now really what I'm doing is I'm beginning to draw ray diagrams, which is important for what you guys are doing, especially next week. In a mirror, you have convex mirrors and concave mirrors. With a convex mirror, the surface bows outward. With a concave mirror, it bows inward. Okay. Now these mirrors reflect. If you took parallel light with a convex mirror, the light is reflected away. And it's reflected away in a pattern where everything diverges. In a concave mirror, the light again is reflected, but it converges. This means that a convex mirror is a diverging mirror. A concave mirror is a converging mirror. So if the image or if the light rays are scattered, it's divergent. If the light rays are focused, it's a convergent. If it's scattering in a mirror, you're dealing with a diverging mirror. Now with these things you look at, if I'm just going to draw these rays for the convex mirror, and kind of exaggerate it. These rays, you can actually draw the line back. And with here, you can obviously see that the points of the rays converge at that point as well. For this and that, we call it F. F is the focal point. The focal point is where the light rays or tracings of the light rays converge. For a concave mirror, the focal point is to the left. For a diverging mirror, the focal point is to the right. And what I'm drawing now is kind of is my axis. When I start drawing mirrors, because you can't really do it accurately, I don't draw convex mirrors and concave mirrors like this. I do it just to demonstrate. Yes, question? What the focal point is? Okay, we're gonna get to all of that. The focal point is where the light rays converge. In this case, they converge here. In the case of the diverging mirror or convex mirror, it looks like the rays are going away from that point. Now when I normally draw a mirror, like when we do these light ray diagrams, I start everything with this. This is what we call our optical axis. And let me actually, I'll draw a better. Optical axis, and then the vertical line is the mirror plane. It's where the mirror exists. Now, because all of us are horrible drawers, sketchers, it's best for you to just draw this out, or just to draw the lines. Don't draw the mirror or the lens. A couple of things that we need to have understood. Mirrors, for a mirror, in the way that we're doing now, if I was allowed to be a little bit more advanced, I would say you could put the object anywhere. But mirrors, we're always going to have the mirror reflect to the left. Objects will always be to the left of the mirror. In our world, it is. So the mirror reflects to the left. The object will be over here. I mark the point with an O. The distance that I use, I call that O as well. So typically the object distance I mark with an O. Not a 0, an O. F marks the focal point. Now, obviously, well, not obviously, objects will always be to the left of the mirror. The object distance will always be greater than 0. You will always use positive numbers for the object being left of the mirror. Now, what if the object is to the right of the mirror? Well, it doesn't make any sense. It won't reflect. If you're behind a mirror, the mirror won't reflect you. So, F marks the focal point. For concave mirrors, the focal point is greater than 0 and to the left of the mirror. What's what? Or is that 0? This is 0. Anything with a slash. No, like on the this is the object mark. Yeah. That's the object distance. Now, here's the deal. When in the book, and in many other places, the object distance, they go d sub O. But when I was taking physics, they said, if I call that the object distance or the object, are you going to confuse it with the number 0? No. because you're intelligent and you understand these things. So with these distances, O I call the object distance, and F I call the focal length. For a concave mirror, the focal length is positive and to the left of the mirror. For convex mirrors, the focal length is less than 0 and to the right of the mirror. So if it is a concave mirror, that's your focal length and that's the focal point. If it is to the right of the mirror, well, this is if it is a convex mirror. Now we have something called I. I is the image. Where does the image form up? And it's also known as the image distance. Images can be formed anywhere. For mirrors, if I is greater than 0, the image is to the left of the mirror. If I is less than 0, the image is to the right of the mirror. So in these types of problems, in lenses and in mirrors, we're given image distances, object distances, focal length distances. Exactly how do we calculate all this stuff? And the equation that we use is 1 over F equals 1 over O plus 1 over I. Remember, once again, that's not a 0, that's an O. So if you take the inverse of the focal length, it equals the inverse of the object distance plus the inverse of the image distance. Now, there's a derivation for this. We're not going to go into it. We're just going to take the product of all this stuff. So let's do a simple mirror. We'll use concave, where focal length is 20 centimeters. An object is 25 centimeters away. Where is the image? The first thing you want to do when you have a problem like this, eventually on the test, you will be given a lens or a mirror. And then you will be given an object distance. And the goal will be, tell me where the image is it magnified, and then describe the image. And we're gonna go into all those descriptions in just a few moments. And then after all of that, I'm gonna get you to draw a ray diagram of what's going on. The ray diagram, a lot of students want to attack that first. A lot of students just want to draw pretty pictures and be done with it. The right way to do it is to do the math first. Do the math first. Do the math first. He did say it 3 times, so that must be important. What you want to do is solve for I. And you get this. Plug in your values. 1 over 20 minus 1 over 25. And if you notice, I am using centimeters. As long as all the units are consistent, all centimeters, all meters, all millimeters, all furlongs, don't use furlongs, but as long as all the units are the same, it'll work. Also in optics, in the lab that you're going to work on next week, you can use either centimeters or meters as long as you're consistent. And in the tests, the preferred unit, unless I ask differently, is centimeters. Centimeters is a number that people can kind of wrap their heads around, and they'll be fine. So this number gives us 100. So the image is positive 100 centimeters. In this particular case, you do use your plus or minus signs based on what's going on. If this was a convex mirror of 20 centimeters, we would use a focal length of negative 20. If it's a concave mirror, we use the positive focal length. In this case, the image distance is greater than 0. Therefore, the image will be to the left of the mirror. Images to the left of the mirror are real. So the location of the image is to the left. Because it's a mirror and the image distance is positive, it is a real image. For a real image, the light converges in a physically possible location. The light physically comes back together at a specific point. For a virtual image, the light diverges, but the rays traceback lines, we'll understand what that means in just a couple of minutes. Traceback lines converge to a point. So if you have to, in order for the lines to meet, if they're physical real light rays, it's a real image. If you got to get the light rays to trace backwards, it's a virtual image. For a mirror, if the image is positive, it's to the left of the mirror and it's real. If the image distance is negative, it is right of the mirror and is virtual. Yes?
Is the image always behind the object?
No, not always. And what's going to happen is, I think I've posted it already. There's a, in addition to the problem set that's due on Tuesday, there's a packet on Blackboard called Optics. In that packet, I go through, there are 4 permutations for mirrors and 4 permutations for lenses, and I go through them all. And so you can see them all there. So this image distance is a positive 100. There's a PDF, there are videos. I'm gonna get all this stuff. I mean, and in fact, what's gonna happen is today we're gonna go through this mirror image problem. We're gonna go through a lens problem. We're gonna go through a compound lens problem. And then on tomorrow in tutorial, we'll do a few more. And I've actually gone through all of these. And I'll start dredging up videos in order to do it, to get that out. So we know about the image. It's to the left of the mirror. Since it's to the left of the mirror, it's real. It'll be fine. You're looking, some of these students over here are just like, oh my God, so much information. It'll be fine. Now, this image has to be described. You've all played with a simple convex lens. You've moved it back and forth in front of objects. You've seen the image that it puts up on the wall. You've seen that the image is upright, looks normal, upside down, or has it been enlarged, has it been reduced? All of these words are coming from one particular equation, and that is m equals negative I over O. I is your image distance, O is your object distance, and M is the magnification. With the magnification, let's do this. Image distance is a positive 100. The object distance is 25. So this is negative 4. The negative is part of the equation defining magnification. Since M is less than 0, the image is inverted. The image has been flipped. And since the absolute value of M is greater than 1, the image has been magnified. So this image has been flipped over and enlarged. So if I ask for you to describe the image, you would say it's to the left of the mirror, it's real, it's inverted, and it's enlarged. So there are 3 basic things L left, R right, R real, V virtual, U upright, I inverted, E enlarged, R reduced.
Dr. Ashford,
Yes.
since the absolute value of n is greater than 1, I mean the absolute value of n is always going to be greater than 1.
Not always. There will be situations where the image is reduced.
Right.
If the object distance was greater than I, which it does happen, it would be reduced.
Okay.
You guys are asking about the permutations of everything, and we've just started. You will end up in a situation where the image is reduced, eventually. All it depends on is mirror or lens, convex, concave, and where that object is. And so I can do all sorts of permutations with that. As I've said before, the key to all of this is before you draw a pretty picture, you get all your information down. So object is 25, image is 100, focal length is 20, magnification is -4. And what I'm going to do is, I'm going to give everybody a few extra seconds to write that down. Good. Actually, I should make a difference of this. Centimeters, centimeters, centimeters. Magnification is a ratio. What's the equation? Since you've asked, you're going to answer it. What's the equation for magnification? -I over O. Units of I are in centimeters. Divide by centimeters. You get, poof, nothing. Yeah, it's a ratio. So now that we've gotten all this written down, what I'm going to do is I'm going to shift this over, and we're going to draw a pretty picture and use my favorite ruler. In this case, what I'm going to do is I'm going to treat that and that as 10 centimeters. So you're going to have to pick a scale. This is my optical axis. This is my mirror axis. The first thing I want to do is I want to mark that focal point, which is 20. Since it is a concave mirror, the focal point is to the left. Now, something that we need to get into practice, and this is a new part of optics, is even though the focal point is over here, I go the same distance on the other side and call it F prime. Sometimes I call it the antifocal point. Sometimes I call it the other focal point. Sometimes I just call it F prime. F prime is useful in terms of geometry on occasion. The object distance is 25. I want to mark that down. Now the magnification, oh crud, I messed this up already. Hold on, I'm gonna redraw it. Well, really the big thing is, and actually I can fix this, is, let me do a better job at this. The scale was all messed up. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Move that one over. That's good. So instead of that being 10 centimeters, I'm going to pick that as being 10. So optical axis, 20 is the focal point. 25 is the optic, or the object. 20, 40, 60, 80, 100. And then the image is there. So really what you want to do as a word of advice is think about the biggest number you got and try to scale everything to that distance. We put in F prime because it may help us. Now, one of the things that we do have is the information about the image, and the image is magnified. So what I do is I draw the image first because it's the bigger one, so I can get the scale for it. It can fill up the entire picture. I'm using that as a centimeter. So magnification 4, 1, 2, 3, 4 blocks. And I drew it upside down. Well, why is it upside down? It's been inverted. It's been magnified, so I make it the biggest image on the whole thing. And I know that it's 4 times as big as my object.
Inverted because it's -4? Or?
Yeah, it's inverted because it's -4. If the magnification is negative, it has been inverted. Done. So I draw my object only 1 block high. And so that becomes this. An object 1 block high with a magnification of -4 becomes 4 blocks high, but inverted. Why is what? Because I make it 1 block high. Yeah, if I decided, let's say I did what I did over here and didn't get the scale right. Let's say I drew this to be 4 blocks high. That means that the image distance, the image height has to be 16 blocks high, which is now off the page. So you've got to you got to reason it out. Do a little bit of artwork.
So your image just has to be proportional to your object.
Mm-hmm.
That way.
Yeah, I'm only interested in proportionality. Yes. Now for this, we're going to have 3 rays. The 3-ray diagram. 1 through the middle. 2 parallel which then goes through focal point. And then the third one is line that becomes parallel. On the test, you'll only be expected to do the first 2. The third one gets tricky. The first 2 are obvious. The third one requires a certain thing to get it to work. So through the middle just means you draw from the tip to the dead center of the optical object. The thing about these is that it becomes a straight path, does not bend. That's kind of a bad word, but what you see is if this was simply passing through, the light would be unaffected. But really what happens is it gets reflected, and what you'll notice is that angle and that angle are the same. So if you measured those angles, they would be equivalent. Now the pair, I know how to get that last one. So the next one is a light ray that starts parallel.
From the origin to the left.
This is how the light ray moves. The light ray hits the mirror, it reflects, and it goes to the image. The light ray, now this is where we have to think about, this is a concave mirror. Concave mirrors bend their light through the focal point. So what happens is that this light ray goes like that. This is 2. And while you're drawing number 2, I'm going to think about number 3.
On the test and homework, do you want us to do this in like different colored pens and everything? So we
Different colors? I mean, if I do it in different colors because it helps me. You could do it because you do whatever. So, the third ray for this. Now, this is why the first 2 rays, you can just knock them out real fast. On a test, you'll only need those 2. The third ray, I'm thinking, I know what it is. They all involve something to do with the focal point. And this is where my drawing, I didn't draw them right. Crud. The third ray goes like that. Now ideally it should have been gone down like that, but what I'm going to do, in order to do it right, I'll look it up. Some of these situations, particularly with the mirrors, the third ray can get tricky. That's why I'm only going to require 2. But for the 2, I guess I may not have picked this correctly, but for the first 2, they were spot on and they lined up properly. That's all I'm going to expect you to do. The third ray is, I don't want that.
What's the second one?
The second ray, you draw a parallel line and then see how this line, the contact point with the mirror, the focal length, it goes through the focal point and the image. And this is why I draw the image first and the object first as well, because I know where they kind of should go, and it really does help. If you've got the math to help you, drawing it is not an issue. In the back.
Yeah, if it's a concave mirror, is that going to bend the light from the object through focal point to the image?
Yes. So really, this is kind of a surface like this. So when it makes contact with this line, it gets bent to the focal point.
Not that one. You go object through focal point to mirror,
Yeah.
one with the hat.
Oh, this?
Right, isn't it gonna bend back to the image?
What, ideally what it should do is something like this, where the light goes from there, and becomes parallel and shoots back. I've got all 8 permutations of this drawn with 3 rays. The third ray, it's no big deal. Yes?
So do the rays always start at the object's position?
Mm-hmm. Really what's happening is that if I had the third ray, 3 photons come off of that tip of the arrow. They all 3 make contact with the mirror, and they all 3 come back to the tip of the image. You could do the same thing for that point, but it would all end up there. So what I do with an image ray diagram, or with a ray diagram, is I draw 3 lines from the tip of the object, and all 3 converge at the tip of the image. The first 2 are no-brainers. Those are easy. The third one, you gotta, I'm gonna go to my notes and go, well, obviously it's that. But like I said, for homework, I'll have it all written out. For the test, I don't expect you to know the third ray. The thing about this, in terms of bottom line instructions on, like, what does this all mean? I saw that you did the math. You got -4, you got an object distance of, image distance of 100. I know it's a mirror because I'm the one who wrote the problem. If it's a mirror and you've got the object to the right, when your image distance is positive, I know you've messed up. If you draw m equals -4 and you draw a smaller upright arrow, you've messed up. So the math guides you on how to draw this thing. If you've got -4, excellent. Draw the bigger arrow upside down. The math is telling you what to do. It's your interpretation of it that helps you.
Can your object be inverted? Can it be upside down?
I don't do that. Technically, yes. So if I had drawn the object upside down and it was an inverted image, the image would have to then be upright. Yeah.
But can you,
But the way that 214 does it, objects are always to the left, starting off always to the left, and they are always upright. And that I keep it simple. All right. The other thing that we have to do are lenses. So where we have concave and convex mirror, a convex mirror takes the light and bounces it away. A concave mirror takes the light and sends it through a particular point. A convex lens, which looks like this, takes parallel light and focuses it. A concave lens takes light and bends it away. So a concave mirror and a convex lens do the same thing. They converge light. So this is a converging mirror this is a converging lens. Convex mirrors and concave lenses diverge the light. So this is a diverging mirror. Concave lens are a diverging lens. Concave mirrors have positive focal length. Convex mirrors have negative focal length. And what you'll find is that if it is a converging lens or mirror, the focal length will be positive. If it is a diverging mirror or diverging lens, the focal length would be less than 0. So lenses are opposite of mirrors in the sense that a convex mirror diverges, a convex lens converges. A convex mirror has a negative focal length, a convex lens has a positive focal length. So start to put together, and in the optics notes there's a study sheet summarizing all this stuff. Whereas in a mirror, I'll draw this right here so you can kind of look. In a mirror, and I'll draw it just as a block, the objects are to the left of the mirror always. For a lens, objects typically are to the left and they're greater than 0. But if they're to the right, and there is a situation where it does happen to the right, the object distance is negative. If it's over here, for a mirror, it can't be here because you're behind the mirror. For a mirror, if the image is to the left, it's greater than 0 and real. If the image is less than 0, it's virtual. Now with lenses, it's opposite. If the image is to the right of the lens, it's real. You could focus a piece of paper and focus light on a piece of paper and you could see the image. If the image is to the left, it's virtual. So those are opposite. For a mirror, the focal point, if it's positive, it is to the left. If it's negative, it is to the right. For a lens, if the focal length is to the right, it's positive. If the focal length is to the left, it's negative. So focal length inverts, images invert. And so you could start seeing the differences between the two. But magnification is constant. So, now one of the things that I understand we're down to 10 minutes. I'll try to get done in 5. With mirrors and lenses, the ray drawing is the same. You both use the same equations. For both situations, lenses and mirrors, you have to use those equations and they don't change regardless. How you interpret them does change. Now there is something before we go, we have to introduce something called a unit called a diopter. 1 diopter, capital D, is 1 inverse meter. One of the things that you see in the real world a lot is when you get your eyes checked and they write a prescription. What does the prescription do? You see like plus 3.0. What is the 3.0 measured in? 3.0 is measured in diopters or inverse meters. If I said positive 3D mirror, and this is where, and for this, just as a little bit of a lesson, for the people who are in the room right now, I'm very happy that you're here, and I can kind of tell a few of your faces. I've never seen you before, but other than that, and everybody looks at you. Don't look at him. He gets self-conscious. By you being here, you're present, and you've shown the interest. And with something like this, I'm going to get a lot of questions about what is a diopter. And if you tell me what is a diopter, I know you have not been to this class, and I know you have not been watching this video. So a diopter, I catch people with this a lot. A diopter is an inverse meter. If you have a positive 3 diopter mirror, is the mirror concave or convex? It's positive. This relates to, you take this and invert it. So the focal length is 1 over that. So the focal length is 1 over positive 3, or 0.33 meters, or positive 33 centimeters. Now if I asked you, you've got a mirror, focal length positive 33 centimeters, is it a convex or concave? It's concave. Is it diverging or converging? It's converging. Welcome to the multiple choice section of test 3. So a lot of this will be like, you got a plus 3 diopter mirror. Is it convex or is it concave? Is it converging? Is it diverging? Another thing you could say is you've got a 2 diopter concave lens. Give me the focal point. When I'm playing with diopters, there will be situations where I give you plus or minus. In this situation, a plus 3D mirror, the plus is required. If I didn't have it there, a 3 diopter mirror, you could say, is it convex or concave? You didn't tell me. You didn't tell me if it's positive or negative. With this, I said it was a 2 diopter concave lens. So the focal length magnitude is 1 over 2 meters, or 50 centimeters. But by the fact that I wrote down on the page that it's a concave lens, is it positive or negative? It's negative. So the focal length is negative 50 centimeters. Because I said it was a concave lens. Concave lenses are diverging lenses. Diverging lenses have negative focal length. When I'm playing with diopters,
So convex lens would be positive.
yes. I either have to put a positive or a negative in front of that number, or I have to give you the specific type. If I just say mirror, there has to be a sign. If I say concave mirror, I don't owe you a sign. I asked these specific questions to my eye doctor, and he said, I don't have a problem with it. Feel free to just ask them away. So I have been given permission by an eye doctor that these questions are entirely legitimate. And to the probably 70 people not in the room, don't tell them. Just throw them under the bus. I know how much of a backstabbing group of thieves you are. So let's just see it happen. All right. Tutorial tomorrow, 2:30. See you then.